Library of functions. Mathematical modeling. Polynomial functions. A polynomial function is a function that can be written in the form f of x equals a subscript n x to the n plus a subscript n subtract 1 x to the n subtract 1 plus a subscript n subtract 2 x to the n subtract 2 plus all the way down to a subscript 1 times x plus a subscript 0, where n is a non-negative integer and all the a's are the coefficients of the powers of x and are real numbers. Polynomial functions of degree 0 are known as constant functions and can be written in the form of f of x equals b. Here you have f of x equals 3, and you see it is just a line where your y value is equal to 3 the whole time, a horizontal line. A constant function has no x-intercept if b is not equal to 0. A constant function is an even function. F of x equals x is the identity function. Its graph is a line through the origin whose slope is m equals 1. It is an odd function. It is increasing over its domain. And there you see the identity function. Polynomial functions of degree 1 are known as linear functions and can be written in the form of f of x equals mx plus b. The last function you saw, the identity function, is a linear function, where b value would be 0 and your m value would be 1. So here are a few different examples of linear functions. Y equals mx plus b. When m is greater than 0, we'll go up from left to right. If m is less than 0, it will go down from left to right. And if it is equal to 0, you have the constant function again. So it's a constant function and a linear function, but it is not of degree 1. A power function is a function that can be written in the form of f of x equals x to the a, where a is a real number. If f is a power function and n is a positive odd integer, then f is an odd function whose range is a set of all real numbers, and the graph of f is symmetric with respect to the origin. The points -1, -1, 0, 0, and 1, 1 are on the graph of f. And there you see three examples of odd power functions. F of x equals x, f of x equals x cubed, and f of x equals x to the fifth. If f is a power function and n is a positive even integer, then f is an even function whose range is all numbers y, such that y is greater than or equal to 0. The graph of f is symmetric with respect to the y-axis. The points -1, 1, 0, 0, and 1, 1 are on the graph of f. And here you see three cases of even power functions: f of x equals x squared, f of x equals x to the fourth, and f of x equals x to the sixth. The reciprocal function, f of x equals 1 over x, where x is not equal to 0. The domain and range are the set of all real non-zero numbers. The graph has no intercepts. And there you see the graph f of x equals 1 over x. Root functions. F of x equals x to the 1 over n, which equals the nth root of x. N is greater than or equal to 2 and is a positive integer. Root functions are also power functions. If n equals 2, f of x equals x to the 1/2, which equals the square root of x and is known as the square root function. And here's a graph of the square root function. If n equals 3, f of x equals x to the 1 over 3, which equals the cube root of x. And this is the cube root function. If you look at the graph, you can see that it is clearly symmetric about the origin. Therefore, it is an odd function. Absolute value function, f of x equals the absolute value of x. It is defined as a piecewise function, f of x equals x if x is greater than or equal to 0, negative x if x is less than 0. It is also the same as the square root of x squared. And because f of negative x equals the absolute value of x, which equals the, if f of negative x equals the absolute value of negative x, it equals the absolute value of x, therefore it equals f of x, and the function is even. The floor function, f of x equals x in brackets that do not have the horizontal part to the top of the brackets. The floor function is also known as the greatest integer function. It is defined as the largest integer less than or equal to x. So for instance, if x is equal to 3.2, x would just be equal to 3. The domain of the floor function is a set of all real numbers. The range is a set of integers. So there you see a diagram of the floor function. The ceiling function, now we're missing the bottom of the brackets, also known as the smallest integer function, is defined as the smallest integer greater than or equal to x. So if x was 2.7, well, the smallest integer greater than 2.7 would be 3. And the domain is the same as it was for the floor function. And here is the graph of the ceiling function. The floor and ceiling functions are examples of step functions. At each integer, the function has a discontinuity. You're not likely going to see the floor or ceiling functions very often, but you will deal with step functions which have jump discontinuities. Example 1. For the polynomial function f of x equals x to the fourth plus 3x cubed subtract 4x squared, I want you to find the intercepts of the graph of f and determine whether the graph crosses or touches the x-axis at each intercept. Well, to find the y-intercept, just substitute 0 in for x. And f of 0 will equal 0, which means your y-intercept is 0. To determine the x-intercepts, we want to set the function equal to 0, factor, and solve. So 0 will equal x squared times x squared plus 3x subtract 4. Factor a little further, we get 0 equals x squared times x plus 4 times x subtract 1. Set each factor equal to 0 and solve. So you're going to get 0, negative 4, and 1. Now we're asked to determine whether the graph crosses or touches the x-axis at each x-intercept. Well, if the x-intercept has a multiplicity of 2, like the 0 does, then it's just going to touch and bounce back. If it just has a multiplicity of 1, it will just cross. So at negative 4 and 1, they will cross the x-axis. At 0, it is multiplicity of 2, so it'll come up, bounce back, and then go wherever it was going. Example 2. What are the values of k for which the graph of y equals x squared subtract 4x plus k will have two distinct x-intercepts? This one you got to think a little bit about. Well, you know it's a parabola. Parabolas open up, open down. If they open up and the vertex is above the x-axis, you'll have no x-intercepts. If it's on the x-axis, you'll have one x-intercept. And if it's below the x-axis, it will have two x-intercepts. So that's what we're looking for, is below. We want a vertex below the x-axis because the a value is positive, so it is opening up. All right, well, if we just had x squared subtract 4x, we know we would have two x-intercepts, because if I set it equal to 0 and solve, I'd get 0 and 4. We also know parabolas are symmetric, and the vertex will be on the axis of symmetry. Well, so the vertex is going to be halfway between 0 and 4, which is 2. So if I plug 2 into y equals x squared subtract 4x, I'd find out where my vertex was if k was equal to 0. So plug 2 in, I'm going to get y is equal to negative 4. So y equals x squared subtract 4x would look like this. Now the question says, for what value of k will we have two distinct x-intercepts? Well, what does k do to the graph? If you recall from what you learned in your previous math courses, that k value is going to shift it vertically, up or down. If it's positive, it shifts it up. So if it shifts it up 4 units, it's going to be at the x-axis, and you'll only have one x-intercept. So we want a value less than 4. Example 3. Find the domain of f of x equals the square root of 9 subtract x squared over x plus 4. Well, how do we determine this? Well, you could do it a couple of different ways, and we're going to do it by determining the domain of the numerator and then the domain of the denominator. Then we'll put it together. All right. Numerator. This is a graph of a semicircle, centered at the origin with radius 3. Looks like that. Okay, so what's our domain? Well, our domain is obvious from negative 3 to positive 3. So you could write it two different ways. Negative 3 less than or equal to x less than or equal to 3, or we could write it as the absolute value of x is less than or equal to 3. Now let's look at the bottom. Well, we know denominators cannot be equal to 0. So in this case, the x value cannot be negative 4. Well, negative 4 has already been ruled out as our domain because it doesn't work for the top, so we don't even have to worry about it. Our domain then is just going to be all numbers x such that absolute value of x is less than or equal to 3. Example 4. A liquid is poured into a container in the shape of a right circular cone with radius 4 meters and height of 16 meters. Express the volume V of the liquid as a function of the height h of the liquid. So here's a diagram of what we have. All right? Well, you need to know a formula. The formula for the volume of a right circular cone of radius r and height h is V equals 1/3 pi r squared h. The formula depends on two variables, r and h. To express V as a function of h only, we can use a cross-section of the cone. So we're going to get rid of this fancy looking cone and just change it to a couple triangles. All right, so here's cross-section of the cone. We know that it is 16 meters high, it is 4 meters radius, and we're looking for it in terms of h and r. So we'll have partial, we'll just use h and r for it instead. So h is our height, r is our radius, and now we look at it, we get two different triangles. We got the big triangle and we got the small triangle. All right, the big triangle includes the small triangle. So similar triangles, I can go r over h, so the radius over the height in general terms, and then the radius over the height in the actual size. So r over h will equal 4 over 16. Of course, you can reduce that, but we want to isolate the r value so we can figure out what h is in terms of that. And so I could just multiply both sides by h. I get r is equal to 1/4 h. So now I'm going to replace r in the formula. So v will equal 1/3 pi. Instead of r squared, it becomes 1/4 h squared times h. And 1/4 h squared would be 1/16 h squared times h would give you 1/16 h cubed times 1/3 would give you 1/48 pi h cubed. All right. So that is the volume V of the liquid expressed in terms of height. V of h expresses the volume V as a function of the height of the liquid. Since h is measured in meters, volume will be expressed in cubic meters. All right, that is it for today.